bottom right corner?
No, it does not.
Oh God, what are you doing? There's not. Why did you get a haircut? There's not room, friend.
There's always been room. This is the same amount of people.
Where's Michael?
It's just because Connor is taking up most of this table right now.
Who's the guy sitting at our table?
Ow, okay. Pro tip, don't stab yourself.
By the way, tell Brian his hair is looking nice because I think he styled it today and it looks great.
I ship it.
Is Mike not here today?
I don't actually.
I don't know.
Yeah, I don't think so.
I don't think so.
Who's not here today?
You know who is here? AJJ.
Oh, I don't know where he went.
True.
He might have dropped.
Wait.
I hope he
Wait, what? Oh, what's your name? Brian, what a prick. Honestly. Wait, what's your name then?
Oh, I switched from sound and light to this. I heard this class split. I'm Fred.
Wait, get it? Because they're going over light?
Speaking of which, that one more fucking sucks.
I would know.
No. Consider yourself lucky. I know every second of it. It made no sense whatsoever. Apparently cows can spontaneously turn into photons.
I'm sorry. What?
I was confused by that, and it completely screwed me over while trying to do this over again.
Okay, so, question, answers, things? Answers, ready?
No, absolutely not. Please.
It says at the beginning of every class you were all sitting around. Why is your little man out?
I just got here.
Owl says confusion just got here. Everyone else has been sitting there like, come on, guys, get your work on the next. Okay, number 1 is 0. Number 2, I have 1.7 times 10 to the 18 joules. I'm using joules. Number 3, I have 1.7 times 10 to the 18 joules. Number 4 is C. Number 5, I have 8.55 times 10 to the 17 joules. Number 6 has 2 answers. I have 2.85 times 10 to the 9 kilogram meters per second and negative 2.85 times 10 to the 9 kilogram meters per second. Number 7 is 0. Number 8 is there is no limit. Number 9 is 2. Number 10 is A and B.
A and B?
A and B, or multiply. And maybe E, but that's kind of up to you. Yeah. 5 is 8.
This is homework 8 or homework 7?
Homework 7.
7.
7?
Homework 8 is already out.
What was 6?
6 was 2.85 times 10 to the 9 kilogram meters per second and negative 2.85 times 10 to the 9 kilogram meters per second.
Sorry, that's what I thought you said.
Is that good? Okay, questions on the homework? You know it, did you get it? If not,
Because sometimes I'm
good. Number 9.
Number 9?
Important one.
Oh my god, do you guys actually get that reference?
Okay. Very important one that is worth going
Okay, so
over. Now let's see this one. We have a cow this time. Okay, so here's how it works. I want to make sure we're thinking about this right. Okay? So you start with the cow. That's a cow. There are his legs now. And tail, horns, it's a bull. Is it bigger? Oh, maybe actually they look more like ears. Okay, so maybe it's half it's fair. Okay, so the arm count is basically just very fast. Pretty sure. Pretty sure. All right, so the mass of the cow is 19 kilograms. So this means that the energy of the cow, if it's just sitting there, is 19 tons. Good. Is 19. Is 19. You might just say kilograms times c squared. Now, if you wanted to work it out in SI units, you may. I think for the answers I did that because I knew you guys would probably do that. But honestly, from now on, this is a better unit to use. Just do it like this. Okay. So, what is the momentum of the cow?
0.
0, good, because it is not moving. Things that are not moving have no momentum. Okay, good. So, when the cow turns into things, right, when the cow decays into photons, then it needs to conserve the total energy and the total momentum. Right? Those two, energy and momentum conservation, are this was faster.
This way.
There's another quarter. You want to go faster?
you have no arms.
That's the new answer. What's the worst thing that can happen? You have one sock.
You already have a beat inside one sock.
There's like 14 million.
Let me read it.
Everybody's arms.
And everything under your feet, so your feet with wet socks on. Talking about the weather is the worst case scenario.
I'm sure you can get worse than that.
Yeah, it can be worse than wet socks. Did your own electricity?
Socks are fantastic when they're not
Micah, is this your laptop?
Yes. Sorry.
Alright, right here. Give me a break. Give me a break. I think it's understandable that I hate anime. The first anime I ever saw was SAO.
Okay, I can understand that.
There you go.
I can play the theme song without a ukulele.
Yeah.
There's good anime out there, but there's also very trash anime out there.
Does anybody do the challenge?
What challenge?
For the homework?
No.
Okay.
Let's see.
Let's imagine the cow turns into a photon.
How? Because
Did you say how? Coolest questions I don't want to understand at this point. If there's only one photon, the energy of the photon would be required to be what?
Same amount.
Same energy, right? That's a simple requirement. However, we also remember what do we know about the momentum of a photon, or the relationship to the energy momentum?
E over C is P.
Good, right? Or E equals PC, or however you want to do it. Right? You remember that? I told you for light. So if that's true, the momentum, if the energy is 19 kilograms C squared, the momentum would have to be 19 kilograms times C. Well, look, the total momentum needs to be 0. Right? So this could not work, and the reason it doesn't work is it violates conservation of momentum. You could conserve the energy, but if you conserve the energy for a single photon, it would have to have the same. It would not be able to have 0 momentum. Photons can't stand still, right? You can't really have a 0 momentum photon, which you should, that should make sense, right? Now, if you want to turn now, so you say, okay, so 1 photon is not possible. 0 photons is also not possible because then it violates conservation of energy, right? Because the energy has to go somewhere. So then you can try 2. If you have 2 photons, which way do you think they'll be moving?
Opposite each other.
Yes, opposite directions. And that is a requirement, also conservation of momentum. So here's the deal, the energy, since these are identical photons, the energy can split in half. 9.5 kilograms C squared for each, because that adds up to 19. And then you can, how can you make momentum work now?
You put it in 2 separate equations with each energy being different.
Good. Now you have to remember that one's negative 9.5 kilograms C and the other one's positive 9.5 kilograms C. And this gives you a total momentum of 0, which conserves momentum. Total energy of 19, so that conserves energy, and everything's cool. It cannot turn into 1 photon. That would violate conservation.
Could it turn into 3 photons?
Could it turn into 3 photons? Sure, why not? Well, if you look at what we did here, right? Could I split the energy into 3 and then have 3 photons going different ways and cancel? I don't see why not, right? You don't have to split the energy equally, you just have to make it add up to 19, and you have to make the momentum add up to 0. That's not a hard thing to do, right? So 3 photons, 10 photons, a billion photons, there's no reason why you couldn't do it, and that's why there's no limit for number 8. Yeah.
For 3, would it make it go 3 into like each like 1.2 between them? So it's like a triangle and also as well, or it'd be like 1 and 2
Both of those are possible, right? So Emily is asking whether you have like one big one and 2 little ones like this, or do you want for 3 if you're doing 3 of them? Or do you want them coming out like a triangle? The answer is both these work. So it doesn't matter. As well as many things in between. Just ask the energy momentum. When you add more particles, you add more sort of call degrees of freedom, basically more things you can change, and that makes it easier, not harder, to fulfill the energy momentum requirements. Sir?
I guess I'm a little bit confused about like how so momentum isn't conserved, but mass.
Sorry, what?
So momentum isn't conserved.
What? No, try the sentence again. I don't like your sentence. Momentum.
Or when it's one photon.
Got it.
When it's one photon, momentum isn't
Would it be
conserved,
conserved, right?
but mass is.
Who cares about mass? There's no law of conservation of mass.
What?
If they taught you one in chemistry, that's because, like most things in chemistry, it works very well as approximation in chemical reactions because the energy scales are too low to cause any substantial mass change. Right? The energy released in a chemical reaction is like a handful of joules. Maybe goes up to kilojoules. Think about kilojoules compared to c squared, right? So the the total mass of, you know, I don't even know my chemical reactions. The total mass of a combustion reaction, like CH4 plus some hydrocarbon plus O2 is different actually from the total mass of the H2O and CO2 that results. But the difference is by such a tiny amount that not even the best analytical balance can pick it up. It's a difference that's going to be on the order of 1 over c squared, right? So we're looking at, and the scale we're looking at is absurd. We're basically looking at, because it's usually kilojoules per mole they measure it, right? So you're looking at something like 10 to the 1 part in a trillion basically difference. So that's why in chemistry you can pretend that mass is conserved and it's fine. But we are no longer in chemistry, we're doing real stuff now. So, that's right, you heard me. They get paid a lot more, so I just got it. And not here in general. So mass is not conserved. Don't even think about it. Okay? Mass is really not conserved. Because that's the whole point. Mass is a form of energy. It couldn't possibly be conserved because it could be converted into another form of energy. Right? Therefore, anytime you try to argue for mass conservation, and you might do it instinctively, so it's very important to watch out for, catch those things that says, oh, these two masses should add up to this mass. Oh, no, that doesn't work anymore. Okay? Mass is no longer conserved.
Are you going to be trying to trick us using that?
I don't actually have to try. Like, I just told you what the trick is, and it's on your homework, and I'm certain some people are still going to mess it up, because not everyone listens to me. And some people do, but it just kind of, you know. Okay, good. So does that make sense? All right, good. So momentum is definitely conserved, that's why this is impossible. Mass, who cares? And maybe you care, but.
Then how would you find the answer to number 7?
What a good question.
If we just say screw mass.
What would be the mass of each photon?
What's the mass of a photon?
Nothing.
Actually, we will actually, in a sense, show that in a more detailed way today, I think.
Yay!
Yeah, why don't we do that today?
Oh god.
Okay, let's talk about momentum. Someone sent me, was it the day, was it you? Someone sent me an email this weekend, those of you? Yeah. About complaining about momentum because you were saying, how can light have momentum if
It doesn't have mass.
mass with momentum is mass times velocity? You know, that is actually not the biggest problem. Let me show you the bigger problem. Let's review a little SI physics, okay? Over here is, what's his name? What's her name?
James.
That's a beautiful name.
What was the number?
John Jacob Jingleheimer.
Jimbo has a mass of
124.
120, no,
5.
kilograms. And Jimbo is holding an object,
24.
and the mass of the bowling ball is 200 kilograms. Sure. Jimbo being strong. Oh, he's on ice skates, of course. And not ice, also.
So he's a weightlifter that can ice skate.
He throws the bowling ball with velocity up. 200 meters per second.
Oh my god.
He's got a good arm.
He's the strongest ice skater I've ever seen.
So, maybe it's a light bowling ball. rocket powered bowling ball in there. So no, it actually he throws it. Okay, good. So let's work this out. Remember how this works? What's the total momentum of this system?
5.
0, because initially he's not moving, right? So initially he and the bowling ball are both at rest. The total momentum of the system is 0. The X gates are frictionless, and so there's no external forces acting. So the total momentum will remain 0, right? He now throws the bowling ball. The momentum of the bowling ball is going to be what?
40,000.
Remember, you multiply those and then count the zeros. 4, 0, 0, 0, 0. Okay. Meters per second. Okay, so that's the momentum of the bowling ball. If that's the momentum of the bowling ball, what can you tell me about Jimbo?
Negative.
Good. Jimbo's momentum is therefore negative 40,000 kilogram meters per second.
What
That's an
happens when this
application
hits the
of
speed of light?
conservation momentum, right? So, therefore, Jimbo's velocity is going to be
Negative 400 meters per
good.
second.
You're going to divide by the momentum, by the mass, and mass is 100, so therefore velocity is negative 400 meters per second, which is also fast. So Jimbo has a good arm, but ends up going quite fast. Okay, good. We all remember how that works?
Yeah.
Good. So that's conservation of momentum in action. Okay, so now let's try this again. Same Jimbo, same mass, same bowling ball, the same mass. The only difference is, let's say he now throws the bowling ball
Half the speed of light.
0.8 c.
He's got a really good arm.
Yeah. Jimbo's been working out.
It's Superman.
So, he throws the bowling ball. Okay, so tell me, what's the momentum of the bowling ball now?
A lot more.
Too much.
Thank you. 160 kilograms times c. Not meant to be the hard part. Okay, so the total momentum of force remains 0. So the momentum of Jimbo is
Negative 160.
negative 160 kilograms c. You
Oh,
want to find the
no.
velocity, you divide by its mass and cancel out the kilograms, and what do you get?
You're a little bit late.
1.6.
Negative 1.6 c.
Wait.
No!
Wait.
Ooh,
I thought I understood momentum.
problematic.
Wait. Velocity is a vector quantity, so therefore that's not the problem. But the C is. Never mind.
C is the problem.
I just saw the thing.
No, it's nothing so simple, I'm afraid. I did everything right. So, I did everything right here. That means something's wrong with our original approach. That is to say, it's not that this was wrong as such, it's that it doesn't apply at high speeds, obviously. Right? Because obviously you can see conservation of momentum very clearly allows you to break the speed of light limit. There's no limit placed on it, right? Okay. That means something else we assume must be wrong. What could it be?
The equation for momentum?
Okay, well, it couldn't be conservation of momentum. Well, it could always be something, but conservation of momentum is actually far more fundamental than momentum itself, because conservation of momentum is the basis of all of Newton's laws, right? All of Newton's laws are really just restatements of conservation of momentum. So, failing that, then what will we have to do? Right. That means conservation of momentum is actually so fundamental to physics that we have to keep it. But what if our definition of momentum is wrong? Okay, now here, you cannot actually rederive this definition. Okay? You can, what Einstein did actually was he did a pretty complicated thing involving Maxwell's equations and Liouville's theorem, and I'm not going to do that for you. Dr. Hopper probably would, because he's crazy. He doesn't mind showing people like graduate level math, level kind of stairs. It's actually kind of interesting, but I don't actually know the proof. So, but I've read it before. What he does is he works this around, he shows that there is a conserved quantity, and then says this conserved quantity, if you slow things down, looks a lot like momentum. And then argues this is probably the same thing as momentum. In the end, though, this is not something you derive. This is something you postulate and check with experiment. This one has been checked very, very thoroughly by experiment. It works. It's momentum. So, it will probably not surprise you though, you know what, I've been sloppy here. Shame on me. I should be calling these U, not me. Why? No. Well, no. Why do I? Because v we've been using for velocity of what? For reference frame. We've been using u as the velocity of an object, right? So, yeah, clearly this is, right, I've been doing it wrong. So, there, now it's fixed. Sorry about that. So now I'm going to do it in terms of u. I shouldn't be using v. V is for velocity of reference frames. I should keep them apart. Okay, so the definition of momentum might not surprise you too much. Can you guess what shows up in it? Gamma.
Gamma.
Let's take a look. It looks like this.
This looks familiar.
Wow.
Okay. Now, do not write down gamma, please.
Oh, why not?
Why not? What is gamma equal to? 1 over the square root of 1 minus
b
squared over c squared. This is not the same thing. It is mathematically identical, conceptually different.
Can we give it the upside down gamma?
Because gamma is used for transforming between two reference frames. And
No.
factors used for that. Most books and websites refer to this as gamma NV. I think that is confusing. I think that is not the right way to do things. It is mathematically the same, but comes from a different source and serves a different purpose. It is just the way. Now, it should be really easy for you to remember though.
Yeah.
Right? So this is just the way to calculate momentum. You know, and you shouldn't be too surprising, right? Hey, let's try it out. So now first of all, you'll notice what happens when u is much less than c.
Well, then it's undefined.
That the denominator, this factor is basically
much
0,
less.
right? And you have basically 1 in the denominator. And then you just get nu, which is classical momentum. So that part checks off, right? Now, let's try this problem again. Now we're saying P is not 160 kilograms C, right? We have to use the full calculation. So it's 200 kilograms times 4/5 C over the square root of 1 minus 4/5 C all squared over C squared.
Again.
Good, so that's 160 kilograms. You notice the top is still the same. The bottom here is going to be.
How does this apply to photons? None of us care. Stop. He's teaching us how to do it.
25, which means we have 160 kilograms C times 5 over 3, cancel, which gives you 800 over 3 kilograms C. Sorry?
Oh, it's kg.
With kg, sorry. Those look like log. That's funny. No, actually, I don't think I do any logarithms in this class. I mean, there's plenty of them in physics. I haven't done much of this class. No, I don't think we need logs in this class. I'm pretty sure things can happen. Things can happen. You never know. Oh, no, it's come up before. But I don't think we'll get to that. We'll see. Anyway, moving on. It's not going to show up in relativity. That answer. Logarithms are not common in relativity. Okay. So that's momentum. Now that means that Jimbo's momentum is also now negative 803 kilograms C, right? Now, to find Jimbo's velocity is no longer simple, right? Because you have to set that equal to this. Well, his mass is 100 kilograms times his unknown u squared root of 1 minus u squared over c squared. Right? This has to be solved for u. Why don't I just do it for you? Cancel out that 100. U is velocity of Jimbo.
8.
So remember, normally over here we did
8 times whatever that is,
velocity, right? That's how we got that.
It's going to be.
Now we're doing the same thing, but the formula for for P is a lot more complicated. So we have to solve this now. Okay, so what we got is root 1 minus u squared over c squared equals 3u over c squared both sides. 1 minus u squared over c squared equals 9 u squared over c squared. So 1 equals 10 u squared over c squared. That means u equals root 10c. Wait, no. 1 over root 10c. Oh, the 8. grab out the 8. Thank you. 8. So over here, the 8. 9 over 64. No longer 10. Alright, thank you. Those 64 plus 9 is 73. Therefore, U equals 8 over root 73 to the C. You notice that 8 over root 73 is less than 1, right? And so you now get the speed of light limit imposed on you again if you use this definition of momentum. Did you see what I did? I went fast because it was that important. I cross multiplied and then squared both sides and then collected the terms of U squared to C squared. You could go review that to help brush up on your algebra. That's a big. Sorry. That is a reasonable question. Yes, and the whole thing should be negative, of course. Yes. Sorry, I've been leaving out the negatives. But really, at the end, you have a double root, right? And you know the answer is negative. So, yeah. So what happens is it's negative here. It's negative here. You square both sides, it disappears. But right here, you have U squared. So you have two roots in your answer, plus or minus 8 over 73, and then you know it's minus from the problem. Okay. So, point is, it works. If you use this definition, now we get a number less than the speed of light. And we're cool. Whew. Hang on. Here's a problem. Okay. You can use the same argument, a very similar argument that are each repeat, and get the same problem if you look at instead of conservation of momentum, you look at energy. Thank you. People whisper and stuff. Yeah, conservation of energy gives you the same problem. You can have something that moves in that has a certain amount of energy when it.
Conservation of energy is completely necessary to the laws of physics.
Yes.
Yeah.
More necessary than anything else.
What about conservation of momentum?
Conservation, and then they go together with energy, probably even more so.
Okay.
So
I can't
extraordinarily fundamental to how physics works. So you wouldn't just throw that out. Once again, it's really, really, really fundamental. So what are we going to do?
Oh, I had a question about the momentum thing that nobody here wants me to ask. What about photons? Since they're traveling at the speed of light, it makes it
undefined. Doesn't seem okay. We'll come back to that.
Okay.
You will today even. Hopefully. All right. So no, we should have time. So energy is going to have another one. This one's not as easy to guess, although you can probably guess a little bit. You know Einstein's equation, right? Mm-hmm. Well, Einstein's equation involves mass, but if you're talking about energy, it really should involve one other quantity. Velocity should be in there, right? Kinetic energy is related to velocity, right? So you'd expect velocity to be in there somewhere. So E equals mc squared cannot be the whole story, and it's not. E equals mc squared is catchy, and thus the world's most popular, most well-known equation, but like it's not the full story. The full story is this.
We're getting the full definition.
It's close. Okay? So this should not be hard for you to memorize.
Of course not.
Okay? So mc squared over over root 1 minus u squared over c squared. So there you see your u factor coming in, right? There's velocity showing up. So it will change with energy. Now notice what happens when your velocity is 0. Then what do you get? E equals mc squared, right? So when an object is not moving, its energy is stored entirely in what form? Mass. Good. When an object starts moving, this factor will always make it get larger, and we'll have additional energy that we usually call kinetic energy. Benji.
We do not have to worry about reference frames for a while.
Oh no.
Hopes and dreams.
No, in a different reference.
Right. Good. When the cow starts moving, its energy will have. If the cow's moving, its energy will have to be different, right? That's good. So let's address Benji's question right now, actually.
Wait. Oh no.
This is not hard, guys. Think about it. Look, a ball is moving here. It has a certain velocity, right?
Yeah.
Based on that velocity, it has a certain momentum, right? Okay, we are now in another reference frame. We see the same ball moving. It will have a different velocity u prime. Agreed? It is different, right? Therefore, what can you tell me about the momentum? The momentum will also be different. Therefore, we can say very clearly that momentum
is relative.
is relative.
Is anything not right?
Furthermore, based off knowledge of its mass and its velocity, you can also find its energy. So it'll have a certain energy. In this reference frame, the velocity will have changed, and therefore
The energy is
energy will have changed. Therefore, energy is relative. But hang on, Dr. Don. Go ahead. Someone ask it. Didn't you just tell us that? Okay, so now we have to be very careful with the nomenclature. What does relative mean? Good. It means very specifically different in different reference frames. Okay? So different reference frames, looking at the same, measuring the same thing, will get different answers. Matt, are you gonna?
No.
So, right. So they're also conserved. But what does conserve mean? Conserve means that energy, for example, is the same at different times, right? You take the total energy here, you wait a while, something happens, then you take the total energy again, you get the same number, okay? So conservation of energy is about, or momentum. Conservation means same at different times. The fact that it's relative means it's different in different reference frames. Okay? So, like Russell said, conservation of energy only applies when you are in one reference frame. That's actually not an unreasonable statement. It's pretty straight. It's actually sensible. The velocity changes, of course, the momentum changes. Of course, conservation is not going to apply across reference frames, right? So, when you're in one reference frame, momentum and energy are conserved. Switch to a different reference frame, you get a different number for energy and momentum. That number is still conserved in that frame, right? But when you're changing reference frames, then the energy and momentum will change. They have to, they depend on velocity. Okay? All right, now let's address this other question. The question of light. So, let's look at energy, for example. All right, notice if U equals 0, then energy equals
MC squared.
mc squared. Good. You can show that if U is very small, but you need BC3 to do it. You can show if energy, if the velocity is small, take a Taylor expansion, and you get basically mc squared plus 1/2 mv squared, plus 1/2 mu squared, which is the kinetic energy term. You can show that, but you need Taylor series, so if you don't know Taylor series, it's not going to help, so I won't show it right now. But you can show that'll work. Now, the big question is, what happens if U is equal to C?
Undefined.
Then you get undefined. Now, let's talk again about what undefined means. What does that word undefined mean? I know it means you divide by 0. But how come there's no imaginary number for division by 0? You ever gone to that? There's an imaginary number for the square root of a negative number. Why don't you have a different imaginary number for 1 divided by 0? Because they're different, okay? There's a difference between them. I'll let your math teacher go to the depths of it. But what undefined means is not that I don't know the answer, but what? Yeah, that's like a physical meaning. Even math, what does it mean?
If you multiply something by 0 and it equals a nothing, another number, then nothing times something is it?
By 0, yeah.
No, like for move this around to the very.
So I know the argument. The argument's good. So what does that mean in general? Therefore, what?
No matter what you input for your thing, it's still going to be incorrect. The equation will be.
Right. So what's the problem? If you divided by 0. The problem lies with the, not with the answer, but with the question. Okay, if I say what's 1 divided by 0, the answer is that doesn't make any sense. You are asking a meaningless question. It is equivalent to asking, what do you find 1 mile north of the North Pole?
Do you mean the magnetic north
What
pole?
is at the North Pole? What do you find? What happens when you go north from there? The answer is that question has no meaning.
Well, there's 2 North Poles, so you mean from one.
There's only one North
There's
Pole.
magnetic North Pole, and then
That's
there's
not a North
geographical
Pole.
North Pole.
That's just a spot on the Earth. There's one North Pole. Right? So you have, I didn't ask which way your compass would point. So that question has no meaning, right? That's what undefined means. So undefined is bad because if the question has no meaning, that means the answer cannot have any meaning either. That's why you put it that way. And therefore, to say undefined, I already told you, means that it physically means what? If you get an undefined answer, then in physics it means that it doesn't happen. So it's not possible.
But
Unless what? Come on, math people, see it? Unless what? Unless mass is 0. Does that change things?
no.
It does. It does. Come on, ModPhys people. It does change things. What's it make it? It makes it 0 over 0, right? What's 0 over 0? What's that called? Indeterminate form. If it's 0 over 0, then it becomes indeterminate. What's indeterminate mean? It's not the same as undefined. Undefined means your question makes no sense. Indeterminate means I don't have enough information to find the answer. It's actually exactly like saying, and soon point this out, I thought it was very clever. It's exactly like saying, what do you find a mile south of the North Pole?
Actually, yes.
No, it's at the North Pole. What's wrong? What's the issue with that question?
Well, which way?
Which way? Every way is south from the North Pole, right? So therefore, right, so it is not, there is stuff south. You can go south. In fact, you have to go south. But it's not clear where you're going to go. It is not sufficient information. Even though anywhere else on Earth telling someone to go south is completely well defined, at that point it's not, right? That's actually a nice illustration of what an indeterminate form is. You can multiply 0 by anything except 0 over 0, no, you can't. Right? But not because it doesn't exist. It's because I don't know the answer. You need to tell me more information. That's what indeterminate form means. You can think of it in terms of limits if you like. And that's the whole L'Hopital thing comes from, really. Okay, so what does that mean? It means that you can do it. It also means that this equation will not give you any answer.
Oh.
It doesn't mean there is no answer. It means that the equation will not give it to you. Right? Indeterminate form just means, sorry, try another equation.
What does the momentum answer give you?
What the momentum equation, if you look at it, what will it give you?
The indeterminate.
Same thing, right? Also indeterminate, right?
Yeah.
So, what does this tell you? To travel at the speed of light, you must what? You must have
No mass.
0 mass. Okay? So now we have a much clearer way of saying why photons must be massless. That's the only way you can travel at the speed of light. If you want to have energy. And by the way, you want to have energy. Because energy is the medium of physical exchange, the currency of physical exchange, if you like. It's in order to affect the universe, you need energy. You affect the universe by exchanging energy with it. And so if you have no energy, you don't exist.
What happened if we had negative mass?
You don't. Yeah. Say it again.
A simple answer.
If the energy doesn't also work, no. You mean infinite mass? No, infinity is not a number. But so you can't. In physics, you can't. Because infinity is not a number. In physics, everything has to be finite. You can't do this if stuff on infinite mass. Physics has no infinity to our knowledge.
Is it also a solution?
I mean, I'm sure, but and you can throw in what happens if you put an imaginary mass. It's just okay, at a certain point it doesn't, at a certain point it doesn't help, right? Because it's not physically meaningful. This is an interesting case in which math comes in and saves the day for physics. Or maybe it's physics saves the day for math. I don't know. Depends how you look at it. All right. So now we understand. Now, by the way, the same thing works vice versa. Because if you had a if you were not going the speed of light and your mass was 0, what would that mean? Then your energy would be 0. What happens if your energy is 0? You don't exist. That's right. Okay. Nothing. Remember, energy includes mass now, right? So if you have 0 energy, you don't exist. So the vice versa version of this is also true. If something that has 0 mass and exists must be traveling at the speed of light. So is it only photons that travel at the speed of light in principle? In principle? No, it would be anything that is massless. Anything massless will go at the speed of light. Are there other things that are massless? Yes.
Information.
What are those? The main one that comes to mind is gluons. Gravitons, if they exist, also are massless if they exist. That's another question. And there are a bunch of particles that are almost massless, like neutrinos, that are really close to the speed of light. Yeah. Yeah. I mean, you can't with this equation. You'll want another equation. I'll tell you the next one. So this is enough for now. Okay, so let's talk a little bit about energy. Energy in relativity, in Einstein's relativity, energy is only allowed to have 2 forms. Okay? Can you tell me what they are? Mass and kinetic. Okay? Mass and mass. We get mass energy and kinetic energy. There is no electromagnetic energy, no elastic energy, no whatever, nuclear energy, etc. Because all of those are really mediated by the interaction of the exchange of particles, and those particles are their own masses and energies themselves. And so if you look in, you zoom in close enough, everything is a bunch of particles flying around. And the only thing that matters, including photons, which mediate the electromagnetic field, right? They're still just particles flying around. So everything comes down to a particle as a mass and a velocity. And from that, you can completely determine its energy. No other forms of energy. They don't exist. No heat energy. So we're talking about particles. And a particle doesn't get hot because there's nothing inside it to get hot, right? If you have something, it's fine to have heat, but the heat is just a motion of individual particles. There's no extra form of term for energy. So because of that, energy actually gets a lot easier in relativity because this is the only thing you need to know. This is all energy, and it's always conserved. Well, it's still conserved that. In fact, the answer, how do you figure out the energy when it's indeterminate? The answer is use conservation, right? And knowledge of momentum and stuff like that will allow you to figure out the rest of it. Okay, good. I feel like there's one more thing I wanted to say. We're almost out of time. Okay, tonight's homework is important, difficult. Okay, it's a momentum problem. You can't do it the way we used to do it. The way you always do this, 2 things collide and stick. That's an easy momentum problem. You've done it all the time. You can't do it that way anymore. Why? Why not? Because when 2 things stick, what do you always assume about the mass of the final object? It's equal to the sum of the previous mass, right? 10 kilograms, 5 kilograms, 15 kilograms. But what does that assume? That assumes that mass is conserved. And what do we know it's not? It's not. So, what are you going to use instead?
Energy.
Energy and?
Momentum.
And momentum. The truth might not be